Right, so today we're going to look at our second day of induction, which is going to follow up with what we did the first day. Did anybody remember the name I gave to the kind of induction we did on day one? I said there's blank induction, which is what we did yesterday, and now there's another type we're going to do today. Yep. Yeah, there's weak induction, which is what we did yesterday, based on just proving a single base case and then going from there. Today we're going to look at what's called strong induction, okay? Also known as the second principle of finite induction. And basically the idea is that instead of just showing a single base case, okay, often we use n equals 1. In fact, we use that for every problem we did. We're going to show the formula works for base cases 1 through k. So that's going to be a big difference when we write our assume step. We're not going to assume today that it works for a specific value of k. We're going to assume that it would work for every single value from 1 up through k. That's a little bit stronger of a statement. Okay? If I tell you that it's going to work for every value up through k, that's more than just saying it's going to work for a specific value of k. Right, but that's how we're going to have to do the kind of proofs that we're going to work with today. Okay, we're going to have to show several base cases, sometimes 2, maybe 3. It just means we have to do a little more arithmetic to start. That's all. We might have looked at this kind of sequence last week. I think we did. It's called a Lucas sequence. There's a famous sequence that has this kind of pattern to it. If you notice the pattern here, you might know the sequence I'm thinking of. Yep, the Fibonacci sequence. Okay, Fibonacci sequence is basically a specific Lucas sequence where the first two terms are 1 and 1. In this particular sequence, the first two terms are 1 and 3. So except for the first two terms, those have to be given. Every other term in a Lucas sequence is found by adding the 2 that come before it. Okay, so if I add 1 and 3, I get 4. 3 and 4 gives me 7, and so on. Okay, any questions on the idea of a Lucas sequence? All right, so we're going to use that above sequence to prove something. And what I want to prove is this. Okay, I'm finding what we call an upper bound for a term. Okay, I want you to prove to me that the nth term of this sequence will always be less than 7/4 to the n power. Okay, so this isn't a formula that's telling me how to get the terms in the sequence. All that it's saying is something like this. Let's say I wanted to look at the, I don't know, let's say the 20th term. If this is true, then I can guarantee you that the 20th term is less than 7/4 to the 20th power. Okay, it's a huge number, but I can guarantee you that the 20th term is going to be smaller than 72,570. Okay? Right, so again, that's called an upper bound. All it's telling me is it's smaller than this. I don't know how small exactly, but it is smaller than that number, the 20th term. Okay, so any questions on what this statement is saying? All right, now we're going to try to show that it is true. So what I've done here is I've written out the first two terms. Okay, a sub 1 is 1. A sub 2 is 3. And I'm telling you that to get the nth term in the sequence, take the n minus 1th term and the n minus 2th term and add them up. Okay, so this is the recursive definition of our sequence, adding up the two terms that come before it. Okay, any questions on the recursive definition there or where I got A1 and A2 from? All right, so let's look at our base cases. a hint we can kind of go by that is if our formula depends on the 2 previous terms, we're going to have 2 base cases. If it depended on the 3 prior terms, we would have 3 base cases. Right? For our proofs, we can pretty much go by that rule. Okay? And the base cases we're going to look at are when n equals 1 and when n equals 2. So I'm going to just write it out a little more formally. So show formula works for base cases when n equals 1 and then when n equals 2. All right, so we know that the first term should come out to what? 1. Okay, first term should come out to 1. A sub 1, I'm just going to write is 1. This is given. Now let's see. Right. So how would I show that as a base case? What would I plug into? What am I trying to show? Right, I'm trying to show that a sub n is less than 7/4 to the n. So I need to know a sub 1. Well, I do. It's given. All right? So a sub 1 is less than 7/4 to the 1. That's what I'm hoping is true. If it's true, I've shown the first base case. Okay? So I needed the first term, which I had. Now I'm plugging it into my formula. If I take 7 and divide by 4 because it's just to the first power, is 1 going to be less than that? Yeah. So this does work. Okay, if you wanted to see what it is, just divide it out. 1 is less than 1.75. Okay. So the formula appears to work for the base case n equals 1. Now we're going to do it for the base case where n equals 2. But to do that, we need to know the second term. Okay, do we know it? Yeah, it's 3. It's given. All right, so a sub 2 is 3. Again, that's given. Now fill that into our formula. A sub 2 hopefully is going to be less than what?
7/4 squared.
That's what this formula is suggesting. All right, and let's fill in a sub 2. All right, so we already know 7 divided by 4 is 1.75. If we square it, we get 3.06, roughly. Is that true? Yeah. So it does work for the base case when n equals 2. Any questions on that? All right, so those are our 2 base cases. And now this is the step that looks a little different in strong induction. Okay, the heading step. Okay, it says assume that our formula is true for all cases from 1 up through k. So now we're assuming that this formula works for a bunch of cases from 1 all the way up to k. Again, k is some fixed positive integer. We can't assume that it works for everything, but we can assume that it works for everything between 1 and k. Okay? At least we definitely proved it works from everything from 1 up to 2. That we know is a fact. Okay, so any question on the difference between how this step is written and how that step is written for weak induction? Okay. So let's write out this step. So a sub k is going to be less than what? 7/4 to the k. Now, I not only can say that that's true, but I can say that it's true for anything up to k. All right. So I can. What would be the term just before k? So is this true? A sub k minus 1 is less than 7/4 to the k minus 1? Yeah. K minus 1 is included in 1 through k. K minus 2 would also be included. So would k minus 3. How many of these do you need to write? Turns out we only need to use these two. Even though it does work for anything up to k, we're only going to need k and the one right before it. And you'll see why in a second. Okay, what do you think step 3 is going to say? Yep.
Prove it for k plus 1.
Yeah, it's exactly the same wording that we had yesterday. Okay, we want to show the formula works for k plus 1. So we want to show that a sub k plus 1 is less than 7/4 to the k plus 1. Okay, so that's our goal. That's what we want to show. Okay, any questions up to that step? All right, now we're going to try to show that. So I need a way to write the k plus 1th term. Okay, I need some way to express it. How can I write the k plus 1th term? Think about what kind of sequence this is and the recursive definition of it. Yep.
A sub k plus a sub k minus 1.
Yeah. If you want the k plus 1th term, you would take the two terms that come before it, a sub k and a sub k plus 1, and add them up. Okay, so that's based on the definition of a Lucas sequence, which we said earlier. That's what this example is about. Right, now from here, we're going to do some substitutions and a little bit of some tricks with it. Oh, yeah, k minus 1, thank you. Okay, we're going to do a few tricks with substitution and a little bit of arithmetic. Now, the next step, I want to replace a sub k and a sub k minus 1. And I want to replace them with something we wrote earlier. What do we usually replace these things with? Where do we look for the information that we're going to substitute in?
In previous steps.
Which step in particular? Step 2.
I know,
Okay.
I'm sorry.
So in step 2, it says a sub k is less than 7/4 to the k. So now I'm going to substitute in 7/4 to the k for a sub k. But it's not an equality. Okay? If I substitute this in for this, okay, and I substitute in 7/4 to the k minus 1, what do we know about a sub k compared to what I just substituted in? It's less. Okay, so this original, this is less than that. Or you could say 7/4 to the k is bigger. I put in something bigger. Okay, what about if we compare a sub k minus 1 and 7/4 to the k minus 1?
Also less.
Yeah, I plugged in something that was bigger. All right, so if you compare this to this, okay, call this statement 1, call that statement 2. Statement 1 is what compared to statement 2?
Less than.
It's less than, exactly. Okay, if I could do this horizontally, I could just keep writing it out, but I'm going to run out of room pretty quick horizontally. All Right? So I just substituted in two things that were bigger than what I originally had, and I used my assume step. Hey, any questions on that? Okay, next thing I'd like to do is factor. Okay, so I'm going to rewrite what I have right here. I'm not going to plug in something different that's larger or smaller. I'm going to rewrite this. Okay. I want to factor out, okay, what I can. And hopefully when I factor out, I'm not going to be left with any exponents that are k's on the inside. Okay. What could I factor out to make that happen?
Would it still be less than not equal?
I'm about to write an expression that is equal to what was at the previous step, which is greater than what was at the previous step. So we're going to end up with a chain of like equals and less thans. And we'll look at what that means when we're done. Okay. So what could I factor out from that statement up above?
7/4.
I could factor out a 7/4. And here's the trick. To what power?
It would be
It's got to be something with a k in it. Not just to the k, but I'm going to factor out to the k minus 1. Okay, so the trick here is you always factor out to your smallest exponent. Okay, so factor out a 7/4 to the k minus 1. And let's see what that would leave us with. Okay, well, what comes after the plus sign? That part's pretty straightforward. What would be left here?
1.
1. Okay, now what would you have to put before the plus sign? Not 1 to the k. Think about what you would have to multiply this by.
7/4. 1. Just 7/4.
Yeah. Because if that was 7/4 to the first, which it is, multiplying two things with the same base, you add your exponents. K minus 1 plus 1, there's your k. And then 7/4 to the k minus 1 times 1 just gives you 7/4 to the k minus 1. Okay, so that step's a little tricky. Okay, but that's what you factor out. So I'm just going to write it as 7/4. Okay, any question on that step? Okay, let's just add these up. What's 7/4 plus 1?
11/4.
Yep. Okay, times 11/4. And now here's a hint. I want to replace this. I want to replace it with something that's bigger than it. But I also want to keep in mind my goal. I'm trying to get 7/4 to the k plus 1. What could I replace this with that would be bigger and help me to get my goal at the same time? Remember, the goal is to get 7/4 to the k plus 1. So just think how you could make this happen in this calculation, and then we'll worry about if it's bigger than 11/4 after. So what could you replace 11/4 with?
3.
Well, if I multiply 7/4 to the k minus 1 times 3, I agree 3 is bigger, but it wouldn't give me my goal. I've got to do something that's going to follow a certain rule to make that my exponent when I'm done.
7/4 to the k plus 2.
Okay, we're a little closer. We're on the right track. I like the 7/4
Or 7/4 squared.
squared.
Because it's k minus 1 plus 2 is k plus 1.
Now, let's see if that really works. Let's see if 7/4 squared
Yeah.
is larger than 11/4.
3.06 with a...
Yeah, you could check it, but it is. There's 7/4.
Yeah,
Squared.
1/4 is less than 3.
That's 3.06. 11 divided by 4 is 2.75. So you just filled in something bigger than what you had before. That's why I put a less than sign. The previous step is smaller than this step. Now my last step, I'm going to simplify what I have right there. Okay. That's going to be 7/4 to what power? To the k plus 1. Now, let's look back at what we have. We have this chain of equals, less thans, equal, equal, less than, equal. Let me show you something with numbers, just like that. Okay, simple numbers. Let's say I had the number 10. I'm going to plug in something less than 10. Okay, then I'm going to do something equal to 9. Let's say, I'm just going to rewrite the number 9. Then I'm going to do something less than that. Let's do less than 5. And I'm going to say that's equal to, I don't know, 50 divided by 10. So now, if you compare this to that, what must be true?
The right side's bigger than the left.
Yeah. Oh, did I reverse my signs on these two? Oh, thank you.
Left side's bigger than the right.
Yeah, the left side is greater than the right. All right, so I said 10 is bigger than 9. 9 is the same as 4.5 times 2. And that is bigger than 5, which is exactly the same thing as 50 divided by 10. So I have these chains of greater than, equals, which means this must be greater than that. Okay, following that chain all the way through. Okay, any questions on that idea? It's like you've seen this idea with the transitive property when you say A equals B equals C, so that means A must equal C. Well, this is kind of like the transitive property, except you're mixing greater thans and equals. Okay? If you do that all the way through, then what's on the left would have to be greater than what's on the right. The key is the inequalities always have to keep pointing the same way. You can never have one that goes back and points the other way. It always has to keep getting smaller at the next step or bigger. Okay? So any question on what we just said there? All right, so now if we look at this, okay, we had equal, less than, equal, and a less than. That means this, compared to this, what symbol would you use? Yeah, is less than. Okay? A sub k plus 1 is less than 7/4 to the k plus 1. That's exactly what our goal was to show. Okay? It involved being clever at a few steps, okay, and plugging things in that would make the math work and keep the inequalities pointing in the same direction. That's the key. Okay? I could not plug something in smaller than 11/4, because then once you reverse the direction of the inequality at just one step, this all falls apart. Okay? They have to point the same way each time. Right, so now at our last step, just write down, we have shown, and go to the original statement. We have shown that a sub n is less than 7/4 to the n. All right, so does anybody have any kind of general questions or thoughts about that proof? All of it? All right, we're going to do another one.
Yeah, that was really
Yep.
Maybe when we see another one,
I don't
we'll
even know
find somewhere.
why you did have to think that you.
Literally, I saw an E.
All right, so
There was no
what's this formula saying? Dominic, can you explain that to me?
And what?
Somebody help Dominic explain what that's saying? Yep.
The first term plus the second term plus the third term. Or like the three before them.
Right. It says
To get that next one.
to get your next term, add the 3 previous terms together. And what they want us to show that this time is that in this sequence, any given term will always be less than 2 to the nth power. Okay? So I don't know what the 12th term is, but I can guarantee if this is true, the 12th term is less than 2 to the 12th power. So it's giving me an upper bound on how big my terms are going to get. Since this formula depends on the 3 previous terms, we're going to go through 3 base cases. All right, so I'm not going to write down that we're given A1, A2, and A3. That's clear. Okay, we are given the first 3 terms. Let's just show the base cases. Okay, first base case is when n equals 1. So that would mean A sub 1 would have to be less than what? 2 to the 1. And A sub 1 is given, it's 1. Is that true? Yep. Okay, so the first term is less than 2 to the n. Second term, A sub 2 would be less than 2 squared. Okay, what's A sub 2? And is 2 less than 4? Yep. So this formula works for the second term. And now for the third term. A sub 3 would be less than, if this formula is true. And A sub 3 is 3. Now, just the first 3 terms went right in a row. 1, 2, 3. Just to make sure we understand, what would the next term be?
6.
Yeah, the terms are now going to start increasing much more quickly. And the next term?
11.
11. Right, so now we're going to be adding up bigger and bigger terms. Okay, any question on the 3 base cases? Right, so now we're going to assume that this formula works for all cases from 1 up through k. Okay, we're not going to assume it works for a specific value. We're going to assume that it works for every value up to k, only up to k. So we'll assume that up to the kth term, it would always be less than 2 to the k. Now, what else can we assume?
You can also assume it is
A sub
a sub k minus
1
1 is less than 2 to the k minus 1.
Sure. If it works up to k, we can assume it's true for the one before k. And because we had 3 base cases, that might give you a hint that we're going to write a third statement here.
A sub k minus 2.
Is less than,
2 to the k minus 2.
yep. Okay. And we could write A sub k minus 3 is less than 2 to the k minus 3, but we're not going to need that. Okay. We had 3 base cases, so we're going to go from the kth term back 3, or back 2. Okay, so we have 3 statements in our assume. Now we want to show the formula works for k plus 1. Okay, what would that look like?
A sub k plus 1 is less than 2 to the k plus 1.
Right. This is our goal. That's what we want to show is true. Okay, and the only way we can do it is we're going to start with the k plus 1th term, and I'm going to rewrite it using the definition of this sequence. How would you get the k plus 1th term?
A sub k plus A sub k minus 1
Yep,
plus A sub k minus 2.
plus a sub k minus 2. Now at this step, this is when we always do our substitution. Where do I go back to look for what I substitute?
Your assume step.
Back to step 2. Now I'm going to make these substitutions, but is it going to be an equal substitution?
No.
No, it's an inequality. Okay, so now we're changing equals to what? Less than. Now, if I'm going to do that, that means what I'm plugging in now is bigger than what I had. Can somebody tell me something that's bigger than a sub k? Should be, yep. That's what we're assuming. Now, I also need something that's bigger than a sub k minus 1. 2 to the k minus 1. And lastly, I have to plug in something bigger than a sub k minus 2. 2 to the k minus 2. Okay, now what did we do at our next step last time?
You factor out.
Factor, yep. So we're going to factor. Now when you factor, is that an inequality or does that create something equal to what you had?
Equal.
Yeah, we're going to now create something equal. We can write less than and equal all day here. That's fine. We just cannot flip this inequality and go back the other way. Okay, so either rewrite expressions that are equivalent to the previous step or larger. That's all you can do. What am I going to factor out?
2 to the k minus 2.
2 to the k minus 2. And what would that, let's start with the last one.
1,
Yeah, it's going to leave me with a 1.
2 to the k.
No, 2 to the first factor.
Just 2 to the first.
And then the other one would be 2 squared.
And the other one would be 2 squared. Because if you multiplied these out and you added the exponents, k minus 2 plus 2, that gives you the k. K minus 2 plus 1 gives you the k minus 1. And then 2 to the k minus 2 times 1 is itself. Okay, now let's add up everything we have. What do I have inside the parentheses? 7. Now, what am I allowed to replace that 7 with? Something bigger than it or smaller? Yes, something greater than. Can anybody think of something greater than 7?
2 cubed.
Okay, you could plug in 2 cubed. And if you do that, 2 cubes, everybody agree that 2 cubed is greater than 7,
Yeah.
right? Let's do it out and see what happens. What's 2 to the k minus 2 times 2 to the third?
2 to the k.
2 to the k plus 1. Now, did we always maintain the inequality going in the same direction?
Yes.
Yes, we always plugged in something that was bigger than the previous step or equal, which means this would have to be less than that. Okay, because we always maintained plugging in something bigger as we went. Now, you could plug in 9 if you wanted here. The problem is it wouldn't give us the goal. Okay, we had to think of something that was bigger than 7, but something that would also give us our goal. But you could pick anything you want. Just make it match up with the goal. So now we can write, we have shown that, and now we're going to switch back to what letter? N, because that N means it's true for every integer, not just up to a certain integer. Okay, it's true for that integer and every one after it. So just write the original statement. A sub n is less than 2 to the n.
Are we ever going to be given the lower bound?
No, I don't think we do one. We probably could do one with a lower bound, but I'd have to look up a problem. It's not one I could just make up. Has to work out nicely to make this happen. Okay, so any question on that? Okay, so hopefully the second time through it maybe seemed a little smoother, but it'll probably still take a little bit of practice to get used to. All right, so the homework, it's not in your book tonight. Okay, it's going to be 4 questions I made up. Some are review from yesterday, and I think one of them, yeah, number 4, let's see. Well, number 3 is definitely a review from yesterday. Number 2 is a review from yesterday. Number 1 is not a strong induction problem. It is weak induction, but the algebra is a little different than what we did. We didn't do any with factorials, I don't think, yesterday.
Is that n plus 1 factorial?
Yep, that's n plus 1 factorial minus 1. Okay, actually, I think most of these are going to focus on the weak induction, okay? Because that's what I really want to focus on for the test on Friday. Okay, even number 4. Okay, I'm looking at that quickly. Oh, well, technically number 4, you do have 2 previous terms. Okay, so as you go through that one, you'll have to see if it works out to be strong induction or weak induction. But that one, now that I'm looking at it, that could work out to be a strong induction problem. Right, let me make it a little bigger so people can see it. And that last part on number 2 says n times n plus 1 times n plus 2 all over 3. Okay, does everybody have number 1?
Yeah.
Okay. Okay, and there's 2, 3, and 4.